This is a response to Sal's video about tau and pi, so if you haven't watched it yet, I strongly recommend that you do. But even if you haven't, I'll quickly explain what tau is. The reason why I'm making this video is because Sal said that the trade-off for using the number tau instead of pi is that the equation for the area of a circle gets a little more ugly, but I think it gets a little more cool, and I'm going to explain why. So what is tau? Tau equals 2 pi. So if pi is 3.14159, then tau is 6.28318. If you want help in memorizing these digits, Weihart has an excellent song about it called A Song About a Circle Constant. How did we arrive at these numbers? Archimedes calculated that when you divide a circle's circumference by its diameter, you always get 3.14, or pi. Therefore, circumference equals pi times diameter. However, most people think of the defining characteristic of a circle not as its diameter, but rather its radius. So the equation gets changed to c equals 2 pi r. And indeed, the radius is used in all types of equations in math and physics and chemistry and so on. But if you divided the circumference by the radius in the first place, you would have calculated 6.28, or tau, and circumference will equal tau times r. So then the area, instead of being area equals pi r squared, would have been area equals 1/2 tau r squared. This, as Sal points out, doesn't look as nice, or doesn't it? In the Tau Manifesto, Michael explains why the new area equation is actually better, and that's what I want to do here. I'll begin by explaining what an integral is. If you graph out an equation, the integral is the area under the curve. This area has tons of applications in physics, engineering, and medicine. But in medicine, we give it a much more intuitive name. Instead of calling it an integral, we call it the area under the curve, or AUC. Here's how we use it and how we calculate it. Imagine a car moving along at a constant speed, let's say 6 meters per second, and you want to know how far it has traveled after a certain time t. If we graph the speed on the y-axis and the time on the x-axis, you can see here that the speed is constant and it makes this rectangular shape. To calculate the distance the car has traveled, we just need to find the area under the curve from time 0 until whatever time we're interested in. So let's pick 5 seconds. If we have a rectangle, then the area is just base times height. And after 5 seconds, the base is 5 and the height is 6, so the car has traveled 30 meters per second. I could make a more general equation here, saying that the integral is the speed multiplied by the time, or distance equals rate times time, which is really just the base of the rectangle multiplied by the height of the rectangle. But what if the car is accelerating? Let's say it's speeding up so that the value of the time is the same as the value of the speed. At 1 second, it travels at 1 meter per second. At 2 seconds, it travels at 2 meters per second. And at 10 seconds, it's traveling at 10 meters per second. Same as before, if I want to know how far it has traveled after a certain amount of time, I just find the integral, or the area under the curve at that time. But now we have a triangle, whose area is 1/2 base times height. So let's look at how far it has gone after 10 seconds. The base of the triangle is 10 seconds, and the height is 10 meters per second, so 1/2 times 10 is 50 meters. Since at every point in this triangle the base will be the same as the height, we could say that the area is 1/2 times base squared, or distance equals 1/2 time squared. The point so far is just that the integral of the velocity tells us the distance the car has traveled. Now in this example, I said that the acceleration is 1 meters per second squared, but let's see how it looks when the acceleration is a bit higher. If we accelerate at a rate of 4 meters per second squared, the base will still be the same as the amount of time that has passed, but the height will be 4 times that. From here, we can see that calculating the velocity at any time is quite easy. Just multiply the time by 4, or the time times the acceleration. So after 1 second, the velocity is 4, after 2 seconds, the velocity is 8, and after 3 seconds, the velocity is 12. And to find the distance traveled, you still calculate 1/2 times base, which is time, times the height. but the height is just the time multiplied by the acceleration. Or in other words, distance equals 1/2 times time times time times acceleration, or 1/2 times acceleration times time squared. And this right here is really the equation you want to know. Distance equals 1/2 times acceleration times time squared. In the previous example, acceleration was 1, so I just left it out. Here, if the object accelerates at 4 meters per second for 2 seconds, then the object will travel at 1/2 times 4 squared times 2, which is 16 meters. You might have also seen this written as distance equals 1/2 times g times t squared, where g is the acceleration of an object in free fall on Earth, or 9.8 meters per second squared. To recap, the integral of a graph is the area contained within that graph. One application of this is we can find the distance traveled by a moving object, in which case we take the integral of the velocity of the object. The equation we found for velocity was velocity equals acceleration times time, and the integral of that equation was distance equals 1/2 times acceleration times time squared. Now, there's a very similar relationship between momentum and kinetic energy. We know that momentum equals mass times velocity, and kinetic energy equals 1/2 times mass times velocity squared. So it turns out that kinetic energy is the integral of momentum. Or let's say that you have a spring with a certain stiffness that we use measuring the spring constant, or the letter K. If you stretch out the spring a certain amount of distance, the force that the spring is exerted is given by the equation F equals K times X. Again, K is the stiffness, and X is the amount that we stretched it out. And now the spring has potential energy stored inside of it, and that potential energy is given by 1/2 times K times X squared. So here you can see again that the potential energy of the spring is the integral of the force that it exerts. Or if you have a capacitor with a charge on it, the charge equals the capacitance multiplied by the voltage across it, and the potential energy stored in the capacitor is 1/2 times the capacitance times voltage squared. So the potential energy is the integral of the charge on a capacitor. And now if we go back to our new area of a circle using tau, we see that area equals 1/2 tau r squared. And this format should now sound like an integral. So what is it the integral of? Following the pattern, it would be tau times r, or the circumference. So the area of a circle is the integral of its circumference, which we can see when we understand that the area under the circle curve is the circle's area. Now certainly somebody could say, but we can do the same thing with pi as well. Of course you could. Looking at a equals pi r squared, we could take the derivative of this and we would get 2 pi r, which again is the circumference. The math works out exactly the same. The point here is that you wouldn't have seen this relationship as clearly. But when you see 1/2 tau r squared, you know that there's a derivative integral relationship involved, just like we saw for 1/2 at squared, or 1/2 kx squared, or 1/2 cv squared. The elegance of using tau, even in the formula for area, is that you can clearly see and memorize and learn and understand that the relationship between a circle's circumference in the area within the context of its radius is the same as the relationship between an object's velocity and its displacement within the context of time, and the relationship between a spring's potential energy and the force that it exerts within the context of how far it has been stretched, or the relationship between a capacitor's stored energy and the charge on its plates within the context of the voltage applied across it. In conclusion, as Michael points out in the Tau Manifesto, even in the equation for area becomes more informative when we use tau instead of pi. The mathematical relationship between circumference and area becomes more obvious, and even memorizing the equation can become more easier because it fits into a well-established pattern from many other need-to-know equations.